faithfully convey value and interpret great books worldwide. Hello, this is Sally Talks Books. Today's book is The Devil Math, subtitled The Power of Mathematical Thinking in the Big Data Era. We now live in a big data era where data permeates every industry, even becoming a key production factor. Possessing rational mathematical thinking is especially crucial. It helps us see truth amid daily complexities and make wiser decisions. The book's English title is How Not to Be Wrong, essentially, How to Avoid Mistakes. The author uses real-world anecdotes to show how mathematical thinking reduces errors. Bill Gates recommended it on his blog, noting how math silently shapes our lives. Author Jordan Ellenberg is a math professor at University of Wisconsin-Madison, founding AMS member and science writer who publishes mathematical insights. He writes for Slate magazine, with articles in Wired, NY Times, and Wall Street Journal. The book has 5 parts: linear reasoning, expected value, regression, and existence. The single quote existence section covers abstract high-dimensional geometry, typically for specialized research. For this discussion, we'll analyze 4 common real-world problems and their mathematical thinking. First, if something's valuable, is more always better? Second, why is successful people's experience hard to replicate? Third, how to judge if the lottery ticket is worth buying? Fourth, why do geniuses often have average children? Let's start with the first question. Is more always better when something's valuable? This mindset stems from linear thinking. Linear thinking assumes proportional relationships between 2 variables. For example, at constant speed, longer drive time means longer distance. More sugar in milk tea means sweeter taste. We say time, distance, and sugar sweetness have linear relationships. So how do we confirm linear relationships between variables? We apply linear regression, a statistical method to analyze data and uncover potential linear patterns. For example, to examine the relationship between admission test scores and tuition at private colleges in North Carolina, USA, we can plot data from 31 private institutions on a coordinate system with test scores on the x-axis and tuition on the y-axis. You'll notice most points cluster near a straight line, showing that higher scoring schools generally charge more. But how much more? Using the linear regression formula y equals ax plus b, we calculate the slope a as 28, meaning each point increase in test scores adds $28 to tuition. See how amazing linear regression analysis is? Data analysis doesn't just clarify relationships between things, but reveals changing trends. It also quickly calculates rates of change. Linear relationships may seem common, but true linear relationships rarely exist in reality, like between salary and work experience. Early in careers, salaries might increase linearly, but as experience grows, salary growth slows or plateaus. So overall, salary and experience aren't linearly related. Determining linear relationships requires rigorous reasoning. Thinking more is always better for valuable things isn't rigorous. Yet linear thinking feels instinctive. We often assume linear relationships intuitively without analysis, leading to flawed conclusions. For instance, media often misuse linear conversion in number games. The Arab-Israeli conflict has been a Middle East hotspot since World War II. News magazines frequently report shocking casualty statistics. Counterterrorism expert Daniel Byman presented stark numbers in Foreign Affairs magazine. Per Israeli military reports, the Second Intifada, 2000 to 2005, saw 1,074 Israeli deaths and 7,520 injuries. For a small country like Israel, these numbers are already staggering. Proportionally converted, it's equivalent to 50,000 American deaths and 300,000 injuries. When you see these numbers, doesn't it make war seem incredibly brutal? Israelis suffered significant losses and casualties. Now, let's look at data provided by Arab-American journalist Ahmed Moore. Ahmed wrote in the Los Angeles Times that during a 3-month military operation at the end of 2008, Israelis killed 1,400 Palestinians. Proportionally converted, That's equivalent to killing 300,000 Americans. But newly elected President Obama remained silent. From this perspective, Palestine also suffered heavy losses, with Palestinian casualties 6 times those of Israel. Here, it's clear that the author is trying to emphasize their stance and mislead readers with linear thinking. Now, in reality, if the US were involved in war, it wouldn't cause so many innocent casualties. War casualties are determined by various factors and have no linear relationship with a country's total population. Proportional conversion isn't feasible, and this linear thinking easily leads to fallacies. For example, if only 2 colleagues are working late in an office and conflict arises near quitting time, with one knocking the other down, does that mean 700 million people in China are knocked down every day? That Such a conclusion is clearly wrong. Linear regression can help us find hidden relationships between variables, but it doesn't mean any 2 variables can be linearly converted.
Right.
And linear thinking is easy to understand, but should not be abused. You might have realized that office conflicts among colleagues are low probability events. You can't extrapolate this probability nationwide. This involves probability issues. The second question, why is successful people's experience hard to replicate? This leads to probabilistic thinking because excelling in a field is a low probability event. When we only focus on the brightest stars and ignore the entire galaxy, survivor bias occurs. Survivor bias refers to when information comes only from survivors, which may deviate from the actual situation. People only see the results after some filtering process without realizing the filtering itself, leading to ignoring key information that got screened out. Survivorship bias was first discovered and proposed by Abraham Wald, a statistics professor at Columbia University. During World War II, he worked in the U.S. military's statistics department. Once, the military approached him asking to analyze bullet hole statistics on aircraft, using math theory to determine where adding armor would be most appropriate. It turned out that combat planes sent out by the military often returned with many bullet holes. To prevent planes from being shot down, they needed to add armor, but too much armor would affect maneuverability and fuel consumption. Neither too much nor too little was ideal. The military hoped to install armor where planes were most vulnerable and needed protection. They wanted Wald to calculate exactly how much armor was needed on those parts. And Wald looked at the data. Engines averaged 1.1 bullet holes per square foot, fuselage 1.73, fuel system 1.55, and other areas 1.8. It seemed the fuselage and other areas were most vulnerable and should be armored.
Yet Wald's answer stunned the military.
The place most needing armor wasn't where holes were numerous, but where they were scarce. Even the unhit engines. Why was that? Wald's logic was simple. Head probability should be equal across all plane parts. Then why so few on engines? Where did those engine bullet holes go? Those holes had gone down with the crashed planes to the ground. The military only counted returning planes. Those that met disaster were ignored. This is the famous missing bullet holes story.
The U.S. military swiftly implemented Professor Wald's advice, drastically reducing crash risks after hits. In a way, mathematician Wald's advice helped the U.S. win World War II. Wald possessed aerial combat knowledge.
His grasp of aerial combat paled next to U.S. officers, yet he saw problems they couldn't. The phenomenon of survivorship bias is almost everywhere in our lives. For example, at training sessions, speakers share how Zhang San achieved millions in sales revenue, and Li Si broke personal records, making this industry seem highly lucrative. But in reality, countless average salespeople exist whose voices go unheard. Why is it hard to replicate successful people's experiences? We often see interviews with successful entrepreneurs extracting success factors. But entrepreneurship is high risk. Many lose everything and lack motivation to share failures. Even if shared, their voices aren't heard. Meanwhile, successful entrepreneurs can elaborately recount their journeys. Whether their success comes from leadership, management, innovation, or seizing opportunities remains unclear. Blind imitation while ignoring missing information often leads to biased conclusions. Conclusion: survivorship bias makes us focus on partial data, ignoring the bigger picture. If survivor data is selectively presented, it lures people into statistical traps. Another statistical trick is actively creating survivors through massive data. Next, let's examine another low probability event: exposing the Baltimore stockbrokers' always rising stocks scam. One day, you get a letter from a Baltimore stockbroker predicting a stock surge next week. You dismiss it, but next week, that stock soars. Soon, another letter predicts another stock's trend. Next week, it happens again. For 10 straight weeks, his predictions prove accurate. Astonishingly so. Finally, he suggests managing your investments. What would you decide? Statistically, with 50% guess accuracy per week, 10 consecutive correct predictions have only 1 in 1024 odds, which he achieved. Against such near impossible odds, wouldn't you trust this investment genius with your money? Hold on, let's analyze this stockbroker's secret from his perspective. In the first week, he sent out 10,240 emails, telling 5,120 people the stock would rise, and the other half it would fall. In the second week, he checks which half received predictions that matched the actual rise or fall. Then, for those 5,120 people, he splits them again. Half predict a rise, the other half predict a fall. This continues week after week. By analogy, after 10 weeks, 10 lucky individuals receive 10 consecutive accurate predictions, thinking he's an investment genius. Such a scam. In today's era of rapid information dissemination, there are many variations and new versions. Essentially, it exploits low probability events to make people see only a partial picture, thus easily believing the so-called truth. In 2008, on a BBC reality show in the UK, magician Darren Brown used the same method to send horse race predictions to tens of thousands of Britons. Finally, he successfully made some people believe he possessed some kind of superpower. At the end of the show, he revealed the secret. The audience suddenly understood the consequences of ignoring low probability events, like giving all Britons a lesson in mathematical thinking. This popular science trick is everywhere in our lives. It works because it's not outright deception. Instead, it uses real information to lead you to wrong conclusions. In this big data era, we're exposed to vast amounts of information and novelty. Behind complex problems, there's often randomness. Faced with complex problems, human intuition isn't always reliable and may even give wrong conclusions. When analyzing data, we must carefully use probabilistic thinking to think comprehensively and evaluate, because the same observation can imply multiple causes. What often misleads us isn't the truth or falsehood, but missing a low probability assumption in reasoning, leading to seeing the leaf but missing the forest. If you have rational probabilistic thinking, you definitely won't believe in getting rich by buying lottery tickets. Now, I need to tell you that buying lottery tickets can actually be profitable. And for the third question, we'll explore how to judge if a lottery ticket is worth buying and understand the underlying expected value theory. If you conduct an experiment, the expected value is the sum of each possible outcome multiplied by its probability. For example, if a lottery's top prize is 5 million, with winning odds of 1 in a million, the expected value is 5 million times 1 millionth. That's 5 yuan. Expected value represents anticipation of the unknown, reflecting the average magnitude of a random variable. When making decisions, calculating expected value helps determine if something's worth doing. Are lottery tickets worth buying? Many would say no, it's just paying an IQ tax. Actually, winning big in lotteries remains a low probability event. Some insist it's worthwhile, sharing strategies like buying small amounts regularly or sticking to specific numbers. When questioned further, they justify purchases with vague probability calculations. And so let's rationally examine the lottery game. Adam Smith, father of modern economics, stated in The Wealth of Nations that lottery operators must be profit-driven. For instance, while prizes may be 10 million, buying all tickets costs over 10 million. Attempting to outbet the issuer is clearly irrational for buyers. Mathematically, buying more tickets per draw increases loss probability. Buying all guarantees 100% loss. Is Adam Smith's conclusion correct? Actually, this statement isn't rigorous. His reasoning commits the linear thinking error we discussed. The relationship between ticket quantity and loss probability isn't simply linear. In fact, buying 2 tickets versus 1 increases your winning probability. As you buy more tickets, winning probability rises while loss probability decreases. This completely contradicts Smith's claim. After a certain purchase threshold, loss probability hits a turning point. Specifically, if you've spent 10 million on tickets, even winning the jackpot means 100% loss probability. So how do we determine if lotteries are worth buying? This requires calculating mathematical expected value. For buyers, money spent is purchase value. Money won is prize value. The award value is what we need to focus on understanding, the mathematical expected value. For example, the issuer sells 5 million lottery tickets at 2 yuan each, with only one winning ticket worth 6 million yuan. So the expected value of this lottery is the probability of winning multiplied by the prize amount. The expected value per ticket is 1.2 yuan. That means you spent 2 yuan to buy a ticket with an expected value of 1.2 yuan. Definitely not very wise. The lottery issue, on the other hand, is guaranteed to profit. The more tickets sold, the more they earn.
So issuers tirelessly persuade people to buy tickets. To judge if a ticket is worth buying, see if its mathematical expected value is higher than the face price.
But what if there's a lottery where the expected value is greater than the ticket price? In the autumn of 2004, Massachusetts, USA, to revitalize its lottery industry and help the government earn more revenue, had the Lottery Center design a new lottery. The rule was, if no one wins and claims the first prize within a week, the first prize doesn't accumulate. Instead, when the jackpot exceeds $2 million, the bonus distributes down to increase the second and third prizes. Right. And with this new rule, even if buyers didn't win the first prize, they could still win big money, boosting enthusiasm for buying tickets. Although the winning probability remained basically unchanged, the increased prize values caused the lottery's expected value to fluctuate and grow. And the price per ticket stayed fixed at $2. A group of MIT students first discovered this loophole. When the jackpot accumulated enough, the lottery's expected value would exceed its price. By calculating the changing expected value, you could determine the optimal time to buy tickets. MIT's James Harvey gathered classmates, and when the expected value was higher than the price, bought 1,000 tickets in bulk, earning triple the profit. Later, they formed the random strategy team, focusing on calculating lottery expected values, and over the next 7 years, profited over $3.5 million. For the issuers, this lottery was still guaranteed to profit. But for people buying tickets when the expected value was low, it was unfair. They contributed to the prize pool for nothing, letting opportunists catch the big fish when expected value was high. For fairness considerations, the Lottery Center discontinued this flawed lottery in 2012. Of course, such flawed lotteries aren't common. Even with flaws, you must buy in bulk to truly profit. Then why do so many still buy lottery tickets? American economists Friedman and Savage proposed a new theory. Measuring lottery returns isn't about objective money, but utility. The same 100 yuan holds different utility for different people. For some, it's an exciting amount. For others, trivial. For an office worker, spending 20 yuan weekly on lottery tickets isn't significant. The loss feels almost zero. But winning the jackpot could directly launch them into a new life stage. Calculated this way, a lottery ticket's mathematical expectation becomes very high, explaining the industry's prosperity. So, are lottery tickets worth buying after all? Actually, such choices are everywhere, from major decisions like college applications and investments to minor ones like haircuts. We can rationally analyze expected returns for every choice. And, you know, however, the utility of returns varies across individuals. Therefore, when choosing, we must calculate expected value while weighing personal utility to make optimal decisions. Being hit by low probability events relies on luck. Yet the world is ultimately fair. Superior genes don't favor one family forever. Geniuses have average children. Why? Part 4 explores regression to the mean theory to understand this averaging world. If you're a soccer fan who stayed up for UEFA Euro, did you notice a phenomenon? Players shining early often perform averagely later. Why? Have they exhausted their tricks? We can speculate. Injuries, jet lag, field conditions, or tactical adjustments. But from a mathematical perspective, this phenomenon is the regression effect. This theory states that whenever a subject is influenced by randomness, regression to the mean occurs. The first to discover regression was the 19th century British scientist Francis Galton. He devoted his life to quantifying heredity, using mathematical thinking to study genetics and pioneering eugenics. Galton focused on studying the relationship between heredity and height. He started with parent-child height data, plotting it on Cartesian coordinates. In the coordinate system, the x-axis showed child height, y-axis showed parent height, and each subject pair was a black dot. After collecting extensive data, the dots formed a scatter plot but revealed no clear parent-child height pattern. Some children of short parents were also short, but exceeded their parents' height. After more data collection, Galton found the scatter plot gradually formed an elliptical shape. The ellipse's center corresponded to where both parents and children were at average height. In his 1889 book, Natural Inheritance, Galton concluded adult children's height regresses toward the mean compared to parents. So if both parents are short, don't worry, your descendants will likely reach normal height. This phenomenon is called regression to the mean, the mathematical regression effect. Galton also studied intelligence heredity. Great scientists and composers' children, while outstanding, rarely surpassed parents' achievements. Geniuses can have average kids. Galton believed intelligence or height are determined by random, internal, or external factors influenced by chance, not always favoring individuals, leading to regression to the mean. For example, some brilliant writers achieve sudden fame under randomness. But when randomness no longer favors them, their performance fades, not from exhausted talent, but the regression effect at play. Or like students who ace a mock exam, but struggle to match that peak performance later, that's the regression effect at work. In short, excellence is hard to sustain. Over time, mediocrity arrives as data gradually regresses to the mean. Hearing this, aren't you wondering, doesn't regression contradict genetics? So, are we still affected by genetic inheritance or not? Galton dug deeper and found genetics still influences us. While randomness affects everyone's traits, its impact varies from person to person. Galton introduced correlation coefficients to explain this. In Galton's charts, ellipses varied. Flatter ones meant higher correlation coefficients, showing stronger genetic influence. Otherwise, regression effect dominates. Correlation ain't just for genetics. Any two possibly related variables can be analyzed this way. Get it now?
Euro Cup stars fighting after hot starts? Not just fleeting brilliance, their performance blends talent and luck, all subject to regression.
How much it affects them depends on their talent, luck, correlation coefficient. So, we've covered 4 mathematical mindsets. Watch for linear traps to avoid big data pitfalls. Probabilistic thinking reveals how impossible things happen with enough chances. When facing choices, calculate expected value rationally while weighing personal utility. Regression helps us stay grounded in this multidimensional world. Math grows from common sense, yet holds unparalleled importance in how our world operates. Strong mathematical thinking helps us truly grasp the world's structure and essence. All right, that's all for the Devil Math today. You'll find reading notes below the audio. See you next time.